Thank you for your time interviewing me. I think the most exciting and pioneer contribution for my lab over the past 5 years has been the discovery of the giant magnetoelastic effect in soft matter, enabling new directions bioelectronics applications. So here, let me give more detailed explanation about it. So basically, the magnetoelastic effect, also named the Valery effect, and discovered by Italian physicist Emilio Valery in 1865, is a variation of the magnetic field of the materials and the mechanical stress. So this effect has been traditionally observed in rigid metal alloy with externally applied magnetic field and has been overlooked in the field of soft bioelectronics for three reasons. So first, the magnetization variation in biomechanical stress range is limited. Second, the requirement of the external magnetic field induce structure complexity and bulkiness. Finally, there exists 6 orders of magnitude difference in mechanical modulus between magnetoelastic metal alloy, and the human tissue. So after joining UCLA, I lead my group in discovering giant magnetoelastic effect in certain polymer system, and later in a liquid permanent fluid magnet. So the giant magnetoelastic effect was further coupled with magnetic induction to invent a soft magnetoelastic generator, MEG for short, as a fundamental new platform technology for building up human body powered soft bioelectronics. So those soft magnetoelastic bioelectronics are intrinsic waterproof, since the magnetic field can penetrate water with negligible intensity loss. So thus, they demonstrate the stable performance in viable implantable manners without any encapsulation. So this breakthrough has opened alternative avenues for practical human body-centered energy sensing and therapeutic applications. I think that is basically a short introduction of my current exciting research in my lab at UCLA. Basically, for soft bioelectronic devices or wearable bioelectronic devices, so why we want to do this type of research? The major driving force that we wanted to replace this equipment at hospital setting in the current healthcare module. So that means in the future, we can deploy those devices into the human body to form this kind of human body aerial bioelectronics network. For example, we want to deploy a lot of sensors which can continue to monitor our physiological information. So to realize this type of so-called personalized healthcare module, I think one of the big challenges that we wanted to address the motion artifact, this kind of concern, because, for example, when you wear some sensors on the human body to monitor heart rate, how about your body movement will cause some motion artifact. So that will reduce the accuracy of the monitoring. So if you wanted to advance those technologies to clinical trial, so I think motion artifact management is a challenge that we wanted to address. And nowadays, this motion artifact management for soft bioelectronics is becoming a very hot research topic. And last year, we published an invited review on Nature Review Bioengineering and had a front cover of the July issue. So in that paper, we have very detailed introduction about the motion artifact management strategies for the soft bioelectronics. So if the audience are interested in this research direction, we read that paper. This is a very good question. I think in the field of flexible bioelectronics, whether it's a skin interface wearable devices or implantable system, so operations often occurs in high humidity environment due to the exposure to the sweat on the skin and also internal body fluid for the implantable bioelectronics. So however, most of the current bioelectronic devices are not intrinsic waterproof. Enhancing their water resistance typically requires additional encapsulation layer, which often increase the device thickness and also degrade the performance and such reduce the sensitivity. So when I began my independent researcher at UCLA, I ask myself a fundamental question. It is possible to develop intrinsically waterproof and fundamental new bioelectronic devices. So to explore this, I considered various natural energy modalities, especially for example, the electric energy, magnetism, heat, and light. Among these, I think magnetic field are particularly promising because they can penetrate water without degradation by humidity. So this led me to invest the magnetoelastic effect in certain matter and its application as a soft and intrinsic waterproof magnetoelastic bioelectronics. So that's the reason I want to pursue this research direction. So to answer your second question, so I think the giant magnetoelastic effect in certain system represent a transformative scientific discovery, yet its full theoretical and experimental potential remains to be unlocked. So our group is deeply committed to pioneer a comprehensive understanding of this phenomena and leverage it as a fundamentally new platform technology to create intelligent and responsive bioelectronics devices. So by exploring this integration across a broad spectrum of applications from bioelectronics to solid robotics, we strive to catalyze breakthroughs that refine the interface between the materials and life, ultimately driving profound societal advancement and the future productivity. I think that is my answer to your question. Yeah. Definitely, yeah. For bioelectronic devices is a highly interdisciplinary research domain. For me, I get my bachelor degree in electrical engineering, and I get a master's degree in biological engineering, and I got my PhD in material science engineering. Now I'm a professor in bioengineering department. So basically, I think those education background give me a very diverse knowledge base to pursue my research. For example, whenever I have some materials innovation, then I wanted to use those materials to build up some devices. So after devices optimized, I always wanted to reach out to the doctors at the UCLA hospital. So we wanted to, can I try those devices on an animal model, or can we perform some human trial to validate the performance of those devices? So you can see definitely for every single piece of the research work I carried out at UCLA, we definitely need a lot of effort contribution from with a background in material science, in electric engineering, in mechanical engineering, and also in the school of medicine as well. Yeah. I think because my research mainly focus on soft materials and electronic devices, I think this is a very emerging and exciting research field. I think our journal our journal could spend more effort, attention to developing this field and publish more papers in this field. I think that's going to be great beneficial to our journal, especially to increase the impact factor and many other parameters because, as I said, soft materials and bioelectronic devices, those are very, very popular research field, and with a lot of people jump into the field, and then that will make the paper will be well cited, and in the meanwhile, they can increase the influence of our journal as well. Yeah. So from my personal experiences, I think set ambitious goals, think beyond boundaries, work with unwavering dedications, and exhibit enduring resilience. So those are very important for the young generation if you want to achieve something, if you want to be outstanding in some domains or in some field, no matter you are doing research or do some other things. I think those qualities are very important. Thank you. Yeah.